So first we're going to do the CTMM speed script, and then from the GitHub CTMM learn, and then after that we'll do, if we have time, the CTMM error script. So this is the first one, CTMM speed. And there's a paper accompanying this method. So when you do distance, straight line distance divided by time, and there's no location error, that's going to underestimate speed unless the data are really, really finely sampled, so that these little straight lines in between the location fixes are approximately true. Because the straight line is the shortest path. So it's not likely to be the true path. The true path's likely to be longer because it's probably not straight, unless you had really finely sampled data with no location error. But when you ramp up the sampling rate, you run into another problem, a new problem, in that from one time to the next, like the wood turtle plot I showed you in the very beginning, then location error, 10, 100 meter location error, from 1 second to the next, that's what you're getting mostly. Now, some devices have a Kalman filter on board. EOPS devices do. And as the sampling rate goes up, I think EOPS, it'll switch over. If you have it at like 1 second or something, it'll smooth its own errors. It's doing statistics on the device. And the errors will go down from like 10 meters to a couple of meters. But and then those errors, since they've gone through smoothing, they're now autocorrelated. Even if they weren't before, they were. Anyways, too much information. For finely sampled data, you have a lot of location error. And let's say you had a device that wasn't doing anything fancy, because that's just making the story more complicated. Then the true track is kind of smooth, but the noisy GPS measurement is not, and it's jumping around. And so if you do straight line distance divided by time, then you get speed estimates that are too big. They're biased too large. Now, if you have a device that's doing something fancy on board, the story just gets more complicated. It could, but let's not think about that. So generally, without any statistics happening on your device, if it's coarse, you're going to underestimate speeds and distances traveled. And if it's finely sampled, you're going to overestimate speeds and distances traveled. And there's a whole paper on this if you're interested in reading. So the method we use is to not do straight line distance divided by time. Instead, we simulate a whole bunch of possible trajectories that are consistent with the data. And then, so then that gives us a sampling distribution for whatever we want to extract from those trajectories, such as speed, the mean speed over the track, or distance traveled. This is very sensitive to two things. It's very sensitive if you have finely sampled data. It's very sensitive to having a good location error model for your device. All right, and that's something we'll talk about later. But let's assume we have that. And then the other thing it can be very sensitive to is if your animal is switching between different behavioral states that are very different in terms of their speed. So if you're, a good example is a bird that constantly switches between flying and perching. If you fit just a single state model, like all the basic models in CTMM are, to a bird that's constantly switching between perching and flying, you're going to get an average state, an average kind of behavioral state out. So here's a case where we simulated that kind of track. There's what the location data look like. Variogram looks nice because this is the variogram. Again, it's an estimate of the stationary autocorrelation versus time. This is time lag. It doesn't have information in it about how the behavior is changing in time. Just the stationary autocorrelation structure across time lags. And here's what's going to happen if you fit a one-state model to something that's two states that are very different. So you get an average state out as your estimate, and when the animal is moving, it's a little underestimating, and when the animal is not moving, it's overestimating. So it's kind of cutting through the middle. All right, so be warned. Without the greatest models, there are limitations. Okay. So this is how it works, and then I'll tell you how good it is in general. So I'm loading the buffalo data, project them, loading the fit that I had. Again, this is the function, so you don't memorize 86,400, which some of you might have memorized that. It's the number of seconds in a day. I'm just going to take a week of data, and we're going to fit a model to a week of data. If you want to estimate speeds, you don't need a long period of time necessarily like you do with home range estimation. Now, you can estimate the mean speeds on a daily basis for most species, whereas for a lot of species you can't estimate daily home range, even though people do that in the literature and publish that all the time. For most species, most larger species, you can't estimate a daily home range for the simple fact that your effective sample size is too low. Like, the animal has to cross its range many times in a day for that to be something you can really estimate. All right. So when you run summary on the fit object, just like this was a Gaussian area and not the KDE area, this is a Gaussian root mean square speed. It's just a nice little summary statistic you can get immediately from the model fit. It's not necessarily the best thing that you can get. This is the still Gaussian, but not root mean square, like the regular mean speed that has the meaning, the intuitive meaning of, on average, how fast were you going? All right, for the model, just from the model, so this is still Gaussian, but it's real mean speed, so 17 kilometers per day. And this is the non-parametric or semi-parametric mean speed estimate, where you're doing a lot of conditional simulations to get a sampling distribution or posterior distribution of possible speeds that the animal might have been doing given this movement model and given this data. So this is much better, or you should trust this much more than the previous Gaussian estimate. It's more consistent with the data. And what happens when we coarsen? So let's say if we remove every other time. So right now our good estimate is about 13 kilometers per day. Now I'm going to coarsen, and I'm refitting the model. It won't take long because we coarsen. This part, the model fitting is faster, twice as fast. This part's slower because when you have coarser data, there's more variation in the simulations now. So this actually takes longer to converge. If you have finely sampled data, this is actually very fast. When you have coarser sample data, it's slower. All right, so we had like 13 kilometers per day before. That's consistent with this, but the confidence intervals have gotten really wide, really, really wide. And it's gone up a little bit. If we try to do this again, fitting is faster. What happened? Still consistent with 13 kilometers per day, right? 0 to infinity is, I'd say. The data are so coarse now, at 3 hours, we can no longer estimate speed or distance with this data. Let's look at what was the selected model. It was OU. This data, we didn't select the velocity autocorrelation. We didn't select the velocity. The data are too coarse to, on average for that week, detect any persistence of motion, any velocity. Might as well have been fractal. It's not fractal, but we just can't estimate the smoothness there because the data are too coarse. So, in general, let's go back to this Mike's paper. Oh, no, that's not the paper. I'm sorry. I thought I had the paper up. I apologize. Here's one example. This is Coati. We did a couple of examples here. But as you coarsen the data, if the data is relatively fine, that's compared to what's the real typical autocorrelation, velocity autocorrelation timescale of the individual's movement. If it's relatively fine, you'll get a consistent speed or distance estimate from this method, barring the first two issues I laid out in the beginning, location error model, non-stationarity not being an issue. And then as it starts to get really coarse, the method does get positively biased, and we just saw that with the buffalo. It was still consistent because the confidence intervals get really wide, but there is positive bias, and then boom, you'll reach a point where the data are too coarse and you can't estimate speeds or with your data, and you just can't get anything out of it, which is preferred. So typically with the data set, people would do straight line distances and say this is speeds, but it's not necessarily really speeds when your data are really coarse. It's something very sampling dependent. Now, what can you do when you have really coarse data? I added this. You have diffusion rate estimates. So you still have a parameter that is your average rate of movement. It's just not speed. It's a diffusion rate. So Brownian motion, Ornstein-Uhlenbeck motion, these processes have diffusion rates, even though they don't have speeds. And then we worked out comparable diffusion rates for the other processes that do have speeds. So you can still compare how much are my individuals moving when you have coarser data, which is about 30% of most GPS data sets. Any questions on that? Yes? Where's the mic?
It's more of a code question, but I ran the courser data and I got speeds and everything, and it gave a faster speed, even though it's coarser.
Yeah, so
Sorry, I was just saying that I ran the code and I didn't get infinity. I got a speed that was a bit faster than the less coarse data. So, and then Alex also got the same as well. So it's not just me. Did anyone else get?
on the third, not the first time, but the next.
The second time we got about 16 kilometers.
You get a different model. It doesn't select the model that it selects when you run the code.
That's On the second time, you guys got a different model. I mean, this is, I don't know. I don't know what to tell you. I'm getting the same thing every time. So I don't know what we did. I don't know what, I have no explanation for that. Do it again. It is sometimes, if the likelihood function is multimodal, I'm not saying that's the case here, but if it is, there can be two modes, and the optimizer for one person will find one and one person find another one if you don't start really close to one of the modes. This is a Buffalo with no location error model in there, are really needed at this granularity of sampling. That tends to be more the case when you have the location error model turned on, because movement and location error can explain the same variance in the data. And so because you have two things that can explain the same thing, then you have an issue of non-identifiability in your model. Which means that something like that can happen. But I don't think that's the case here. I'm not.
I think what's happening is you're running twice the sub, so you make it even less quantity of. So you run 2 times the.
Mike?
Oh, sorry. So in the 45 line, basically you run that one again, and it makes it a coarser, and then you get the new. So you're doing it twice.
Yeah,
like
I'm not coarsening.
No. Like for a second time,
Yeah,
if you do
I
it,
coarsened
then
again.
that's when you get the infinite. I
Yeah.
think we just skipped that.
Oh, you guys didn't coarsen again.
Yes.
Yeah, that's what I thought. Yeah, if you didn't coarsen again, you got to coarsen twice before it's gonna. Yeah. And here going from, actually I said 3 hours before, but we went from 1 to 2 to 4. So Friday, when you do step selection functions, you'll coarsen to 3 hours, I think Bjorn will have you do, which is why I said that. But here we actually coarsen to 4 hours. Okay, that's resolved. All right, and we've got time for interactions. Oh, I said we do the error script next, but I meant interactions. Okay, so these are a few of the interactions you can estimate in the package. Load the package, you're going to load the buffalo, their fits, and their AKDEs. So home range overlap, there's a paper on that. There's a help file on calculating the overlap. We can calculate overlap for this list of AKDEs because they were calculated on a consistent grid with one call to AKDE. A common error people will run into is that they'll loop and calculate AKDEs individually, which is fine, but then they won't have a consistent grid, and then you'll get an error, which I'll show in a second. So here, I'm calculating two AKDEs separately, so their grids won't match at all. And then I'm running overlap after doing that, and it complains that the grids aren't consistent. So you can either run AKDE on everything with one call, or there is a grid argument to AKDE, and you can specify how you want your grid to be. They don't have to be exactly the same. They can be like this, but with the same resolutions and the same and aligned. Yes?
So what are the memory limitations in terms of how many individuals can I put in there? How many AKDEs can I fit at once?
It should be fine. The problem
So
people
could I fit my 600 AKDEs?
Yeah, it'll be slow.
But
I mean, I don't
so the RAM, will that run out of memory pretty soon,
No.
or is it not requiring?
No, I'll tell
RAM?
you when it runs out of memory, and I think Mark might have ran into this at some point. Here, let me pull up the help file. I put this in for people in the grid argument. There is one issue that I haven't fully coded around. I do have something like a stopgap solution. In that, if you got a bunch of individuals and you want to calculate them on consistent grids, that means the same resolution. But what if like one individual is a resident and lives in this little room, and another individual is like commuting between countries, right? And the code I have by default chooses the best resolution, which means the highest resolution, and the largest extent for each individual that you need. So that individual that's traveling between countries, if you give them the resolution of an individual that lives here in this little room, then you'll run out of RAM. So I put in this option so that you could, instead of saying using the minimum resolution of all the individuals, you could do something else that would be larger and you won't run out of RAM. What I really need to code, I just haven't gotten around to it, is composite resolutions, to where the biggest one would be some multiple of 2 to the n times the smallest one, so that I could put them on the same grid appropriately without losing detail. Each would have their own resolution. They would just be composite. I'll code that eventually, but this is my stopgap solution. Just blow up the resolution. Because if you're going to calculate like overlaps or something, you don't need all the detail of this to get the overlap between this little one and the big one. Yes?
Does it matter which method you use to estimate the AKDE, or can you compute overlaps with different AKDE methods?
Yeah, it's fine. It doesn't matter. All right, so this is what you get out.
Sorry,
Yeah, I'm
just a
sorry.
question. Is it just a spatial overlap or a temporal overlap as well?
This is just a spatial overlap. I'll
Okay.
talk about temporal overlap later. Yeah.
Is the overlap looking at the overlap in the home ranges
Yes.
or the utilization distribution?
Yes.
Okay.
Yes and yes.
Yes, yes.
Yeah, and then there's different, in the statistics literature, there's different overlap measures. And there's an older paper by Fieberg and Kokanee where they looked at this and they concluded that basically 2 of these are good, look pretty good. And we came to the same conclusion, except that we went one step further with the statistics. And of the 2 ones that seem pretty good for our use and comparing home ranges, the Bhattacharya coefficient is the one overlap measure that not only is it good, it has all the nice properties that you want, but also we could work out a bias correction for it. So if you just calculate a KDE or anything, and let's say it's pretty decent, and then you calculate an overlap measure from that, what's going to happen is that more often than not, random noise will create more separation between the distributions than more similarity. Right? You have a natural bias. And with the Bhattacharya coefficient, we could correct for that. So there is a debiasing, like 1 order of debiasing in this method. And it's the overlaps between 0 and 1. 0 means that the distributions have no shared support, which may or may not be what you're interested in, because this, let's say these distributions are very compact, like they don't go really far. This overlap is 0 and this overlap is 0. Okay, so keep that in mind. There's no difference between this and this with these standard overlap measures. And then it's 100% if the distributions are identical. So here you have a table of overlaps between individuals, lower and upper limits, and point estimates. If you just want, yes?
So just to clarify it in my head, if that BC value,
Yeah,
if it's 1, is that 100% overlap?
100% overlap. Their distributions are the same.
So I can say they shared 100% of their space use.
Yep.
Okay.
Yes.
I have a question. I think I missed it, but where is it the fit and the home range is coming? Like, do we need to calculate it before?
Yes.
Okay.
So you run through all the analysis you've done. You have your home ranges, your AKDEs, and you feed them in. You just feed them in as in a list into the overlap function. That's all you have to do. 1 line.
And how about the fits?
How about what?
The fits? It's the models. The
You've
best
already.
models.
So the model fits are actually stored inside the AKDEs, and they do get used here. They get used to propagate the uncertainties. So these overlaps have confidence intervals, and also for the bias correction as well. There's a Gaussian reference function bias correction. Yeah. So you don't need that as an argument because it's in the object. Was there a question here as well? Microphone's coming.
I feel like you're going to talk about it, so I was just going to wait.
Okay. Hold the microphone just in case. All right, so it's easier. That's a huge table. It's easier if you just want to look at 2 individuals to name them, and then you get the confidence intervals for the overlap. So point estimate 70%, but somewhere between 40 and 95%, basically. Lots of uncertainty in the overlap because there's lots of uncertainty in their actual distributions because their effective sample sizes are not very high. Yes?
Are these overlaps directional?
Directional. What does that mean?
So for instance, if I had a really big range and you had a smaller range and our ranges overlapped, the amount of overlap from my side to yours would be proportionally less given the size of my range.
Yeah, so these overlap measures are symmetric.
Okay.
The ordering doesn't matter. And in all the standard statistical measures of overlap, that is the case. I am aware that in wildlife ecology, a lot of people will calculate geometric overlaps from the coverage areas that are asymmetric. How much of one is in the other, how much of the other is in the one. We concluded that that's a bad way to do things, and then Fieberg and Kokkinen concluded that's a bad way to do things. Because that method, it's nothing you find in the statistics literature, first of all. That's already a red flag. And then also it's sensitive to what's the probability of your coverage area. If you do a calculation at 50% coverage, if you do a calculation at 95% coverage, you get different answers. And then whereas with these statistical methods, they're comparing the entire distribution. So they're comparing the full non-uniform space use, right? The whole things, and not just one flat area that gets a certain probability of use.
I
Yeah,
have a
yeah,
second
please.
question.
Yeah.
If you wanted to use these estimates as a response variable in a model, how could you incorporate the confidence intervals along with the estimate?
There's a couple ways to do that. The easiest is the metaphor package. The metaphor package allows you to do meta-analytic regressions. Let me answer a more general question. I'm not sure if I have overlaps in here. I don't think I do. Overlaps are a little more complicated. Let me talk about other variables where the story is simpler. Let's say you had home range areas and you wanted to use those as a response variable. You can either take the home range area point estimates and the variance estimates out of the model fits, and you could put them into a mixed effect model that you may or may not know how to code up with a family that respects the fact that home range areas are scale parameters between 0 and infinity. Or this gives you a little more options. You can use the log function and you can say what variable you want to extract. Overlap is not in here yet because of a complication that I'll tell you. But you could say area, you put your model fits in here, you say area, and it'll give you point estimates of the log of the areas. So now it's kind of normalized, and also the variance of the log of the areas. And then you can take that and you can put it right into basically anything, like the metaphor package, and you could look at how does log of area depend on different predictors, and the uncertainties will be in there. The metaphor can handle the uncertainties. If you're good with mixed effect models, you can also put in uncertainties and your response variables in mixed effect models. It requires knowing how to do that. Whereas the metaphor package, it just goes into an argument. Right? It's really simple. Overlap as compared to all these parameters. Overlap, there's a little more complicated, possibly, because if you were to take all the overlaps between all the pairs you have more pairs of individuals than you have individuals. So there's correlated errors. If you were to use all the pairs, that's really, your 3 by 3 pairs is really just 3 pieces of information repeated, basically. And so those confidence intervals alone are not enough information to account for that. And I just haven't sat down and worked that out. But crudely, you could do it in the same way as this, and then just go, okay, I got 9 of these overlaps, but I only have 3 individuals. So let me just post hoc expand the end state, the end output, terminal output confidence intervals by a factor of the square root of 9 over 3 or something like that. You could do a post hoc correction for the non-independence. That's probably the easiest thing you could do.
So, Chris? Sorry.
I'm saying we have a paper in review where we did some analysis on overlaps, and the meta function will work with overlaps. But in that case, we weren't aggregating a bunch of overlaps of many individuals. We were aggregating a bunch of overlaps of many, like A/B comparisons, like before overlaps between territorial individuals before their encounter and after their encounter. So those were independent of each other. And in that case, with that kind of analysis, where the overlaps are independent of each other, it would be very trivial for me to extend this to an overlap, and then for you to be able to do a meta-analytic regression or mixed effect model. Yes?
I have a question still about the overlap results. So there are some species that the male has huge home ranges, and within the home ranges there's entire home ranges of females. So if you calculate the overlap, and if you calculate the overlap of what you also said, like of a big home range that is like completely covering a small one, what do the numbers then look like?
It's the geometric intuition of what fraction of the big home range is the little home range.
Okay, so it's always the bigger, how much of the smaller, or?
Roughly speaking, so if you have uniform distributions, it boils down to the intersected area divided by the geometric mean of the two areas. So it's less than 1, is what I'm saying. It's a fraction of 1. So if you want, and I've heard this from multiple people, if you want something that gives you 100% in that case, then you got to figure out how to tell me what that means mathematically that you want. And then I'll do it. But no one's been able to, there's like a communication gap here between what people want and what I can implement. And we haven't crossed that divide yet.
Okay.
And maybe that means that divide can't be crossed. Maybe that means that doesn't make sense. Or maybe it doesn't. I don't know.
So I think if I guess what Anne was saying is, because I have a bigger distribution with a smaller distribution inside, they are not overlapping 100% because there's just like a little overlap over the big overlap. But it's telling me a fraction of the big overlap that I'm occupying if it is everything inside.
Yeah.
Correct?
Yeah, so in statistics, these measures are called overlap, but they're also called similarity. And I think similarity is more precise for non-statisticians, that these are really how similar are the two distributions. Okay. We don't have a lot of time before dinner. I'll say, Mike's going to be mad at me, but I'm going to skip this to go to proximity. I'll say there is a function for if two animals have some overlap, and they're moving independently, and let's say they encounter each other, what's the distribution of where those encounters would take place? There is a function that can calculate those distributions, CDE, conditional distribution of encounter. And I'm not going to run this, but if you want to talk about temporal overlap, like are they at the same place? There's a function called proximity. And what proximity is going to do is it's going to give you a statistic estimate that's going to be between 0 and infinity. And it's basically how far away from each other are the two animals on average compared to what you would expect if they were moving independently. So if this proximity statistic is 1, that's consistent with them moving independently. If this proximity statistic is less than 1, and it has confidence intervals, if this proximity statistic is less than 1, then they are closer together on average than you would expect for independent movers. And if this proximity statistic is greater than 1, then they are farther away from each other on average than you would expect for independent movers. And this statistic is, I made this as an improvement over, some people look at pairwise correlations in the steps or the velocities. And if you can do that, but that can have really non-intuitive, that doesn't necessarily have the interpretation that you might think. You might think, oh, if they're correlated, that means they're moving together and they'll be closer together most of the time. But that's actually only true when their home ranges are right on top of each other. If their home ranges are far apart, then anti-correlation will actually get them closer together more of the time than positive correlation. So this statistic, this proximity statistic, is more what you want to know. Are they encountering each other? Are they getting close together? Or are they avoiding each other? And I'll stop for questions and dinner. It's 6 o'clock.
So special, as we said, similarity, so maybe may work better than overlap for maybe our understanding.
Yeah.
I'm thinking just like large leopards, mainly you can have more than one female inside the home range of a male leopard. Then that will give me a value of how much of the male range the female is actually using, let's say. That's okay.
Yeah, I've not seen anything in the statistics literature that corresponds to what you guys want. I just haven't seen it. I'm sorry. And I can't formalize it in my head mathematically either.
Yeah, I guess we have another, when we hear overlap, we see two polygons.
Well-
and then it's like this, how much, what is the proportion of this overlapping with this? And so what you said before.
I'm not the first person to use statistical overlap measures on tracking data and use that name, so can't blame me.
No.
There's another question?
If we want to do the overlap across the season, so to see with the same individual, will also be possible with the same, because it will have the same name and fit.
Yeah, well, you would in the list you would name it summer, winter, or something like that.
Ah, okay.
Yeah. And then you can use the meta function to average those overlaps across individuals because they would be independent of each other. You could do that as well.